Hello and welcome back to my channel. So in this video, continuing on with the ultrasound listening device, we will talk a little bit about automatic gain control, which is a useful feature to have for the microphone amplifier. If, say for example, your source of sound is close by and then changes to further away, moves further away. Without automatic gain control, you'll notice the intensity of the sound is dropping as it moves further away. So it would be nice to have a circuit that will compensate for the drop in the microphone preamplifier output, boost it up as the sound moves further away, and lower it down as the source of sound moves closer in. So how are we going to achieve that? Well, let's start off first with just discussing the operational amplifier. So we have, let's say we have a operational amplifier with a inverting input sound source, signal source configuration. So we have input resistor, feedback resistor, back to the inverting input from the output. And we're going to ground the positive or the non-inverting input. And so the input is in here, and the output is taken from there. So we'll call this R1 and R2. Well, this is a fairly static circuit in the sense that the output to input relation is simply given by the negative of the R1 over R2 ratio, which you can probably find in many operational amplifier textbooks. But now let's say that we can vary R1 as a function, make it dependent upon the output level. So it's not manually variable, but it's going to be variable through a control voltage of sorts that is a function of the output level. So how do we do that? Well, let's just redraw this circuit with something else in the feedback loop of the op amp. So I will draw it here again. So R1, R2 is going to remain same as before. Grounding the non-inverting input. So we will still have a resistor, feedback resistor, that is static, taken from the output back to the inverting input. And now, in addition, without getting into the other kinds of details, we're going to use something called a operational transconductance amplifier, which sort of has a similar symbol to the op amp. It's still a triangle. It has a inverting input, non-inverting input, but also has an additional symbol with a control pin. The output of this Operational Transconductance Amplifier, which I'll call it OTA for short, is fed back to the junction of this static R1 resistor and the R2 resistor in the feedback loop of the op amp. Okay, so what do we do with the inputs? Well, okay, so we'll take the positive non-inverting input, connect it through a voltage divider to the output of the op amp. We won't worry about what the value of that is for now. And sort of to balance out the offset currents or offset voltages, we'll place exactly the same parallel combination of resistors, single value resistor, but equal to the parallel combination at the non-inverting input at the non-inverting input. So this one is the value of the parallel of those. So usually, let's see, let's call this R3, R4. Usually R3 is much smaller than R4, so you're stepping down, you're knocking down the output quite a bit to feed it into the OTA. So one OTA of choice that I am using, is called the LM13700, and it has one additional pin called a diode bias input, which well, we won't discuss in detail at this point, but it is to linearize the operation and reduce distortion of the OTA. So the output of the OTA is a signal proportional to the difference of the voltages between the inverting and non-inverting input, but it's not a voltage, it is a current. So it produces a current that is pretty much independent upon any resistor you place in the output path here. And the output current, say I/O, is directly controlled by an input current into this control pin called the amplifier bias current. So as the amplifier bias current goes up, the gain, the transconductance gain, in other words, for any given signal at the output level, the output current goes up. Okay, so what's happening here? Of course, we have a current through this feedback resistor as well, but from the point of view of the op amp, well, what's happening? Let's say, for example, the output signal is very low, and the current output of the OTA is also consequently low. If you have a low control current flowing into this pin here, the gain of this op amp is pretty much dominated, just like before, by the ratio of R1 and R2. But as the output signal rises, or let's say, for example, leave out the output signal, let's say, for example, we change the input amplifier bias current, we increase that to increase the output current of the OTA. Of course, the output current is directly proportional to the output voltage that's appearing at the output of the op amp. So it's a signal current. In other words, it's not static. So what's happening is the current that is feeding into this junction of the op amp is increasing. So that, in effect, is very similar to changing the value of the overall feedback resistor in this branch of the circuit. So from the point of view of the op-amp, this OTA appears as a voltage or current controlled resistor, where you increase the input current, the resistance is going down because the output current is increasing. So this is in effect how to control the gain of the op-amp through an use of an OTA, an Operational Transconductance Amplifier. So now, how do we want to control the amplifier bias current? How do we want to control the gain of this branch here? Well, what we want to do is we want to sample the output signal of the op-amp and feed it into something called a peak detector. So as the sound level is going up and down and so on, what we want to capture is the peak, the envelope voltage of the output, and so on. So what kind of circuit do we use for that? Well, it's kind of very simple, or it's more or less out of a textbook that you can probably find on the internet, but it's called a peak detector. I'm drawing my op-amps a little bit elongated here. I'll just draw the circuit right here. So first of all, at the input to this op-amp, bring this up a bit. I think it's getting out of view. We'll present a low-pass filter, sort of a capacitor and resistor, to filter out any sort of floating DC that might be present on the output of this op-amp here. So these are, incidentally, I like to use TL074s, JFET input op-amps, and I can give you a few pin numbers here, so that way we know what we're referring to. Okay, so we feed the output of pin 1 of TL074 over here into this low-pass filter, and let's put a few diodes in. Sort of briefly explain how this works. Okay, so the diodes I'm using are 1N4148 signal diodes. Pen is not cooperating very well. I think I have to get a new one. Okay, so for the as the voltage swings of the microphone preamplifier output change about a DC value, this diode here is going to pass only the positive current peaks, and we'll pass it through a resistor and another low-pass filter, capacitor, ground with a parallel resistor, So I'll give you the values right here. This one's 220K, and the capacitor is 0.47 UF. And this one here is 20K. I've already built this, so I'm just reiterating everything. And then we take the output, or the voltage level, across this capacitor, and we buffer it through another op amp. Positive input. So, incidentally, what happens here is all the negative voltage swings are fed back through this diode back to the non-inverting input. So this is basically a positive peak detector circuit. And okay, we have an inverting input that we take the feedback directly from the output here. Oh, not cooperating very well. I think I have a blue one here. Might do better with it. Okay, there we go. Okay, and in addition, we will also place a 100K resistor between there and there. Okay, so the action of the circuit is such that this capacitor charges up very fast through this 20K resistor on the positive peaks of the voltage swings, and it discharges slowly through the larger one, 220K. In other words, sort of it keeps the peak, it holds the peak for a little while. And so what do we do with the output here, which represents the envelope level of the output? Well, we're going to feed it into a transistor through let's go through a resistor. And another resistor to ground. And okay, without drawing too much what we're going to have up here, the idea is I have a resistor here, let's say it's 2.2K ohms and 2.2K ohms. Maybe this one's not required that much. So I get one diode drop across the base emitter junction, but basically what I'll have appearing at this junction between the emitter and this 2.2K resistor is the envelope voltage that we're drawing up there, sort of, etc., shifted down by one base emitter drop by minus 0.7 volts. So by controlling the value or selecting the value of this resistor here, I can actually set the current being drawn from the collector emitter passing through from the collector to the emitter of this transistor, pretty much independently of what is happening elsewhere in the circuit. So we're almost on the path to developing a current source here. So the current I here is pretty much the peak voltage minus 0.7 volts, the diode drop, divided by the 2.2K resistor value. So basically what I've created here is basically a current that will pass through this transistor that is dependent on the envelope voltage of the output signal. So what we were discussing previously is I need a control current fed to the OTA, preferably a control current fed to the OTA that is proportional to the output signal voltage. And here we're on that path. So we're not quite done yet. So in addition, this transistor will be, I'm just going to show it in block diagram form. It's going to drive, because I don't have enough paper here, it's going to drive a current mirror. So a current mirror it's connected to V+. I'll show it on a separate piece of paper. There's two V+ terminals, or one, doesn't matter if you connect one internally. And it has a branch, output branch, that creates a copy of the current passing through this branch here. So this branch is pretty much the same copy of this current. There's a little bit of a base current that is contributing to the emitter current, so they're not exactly the same. But for the most part, the collector current of the 2N3904 is the same as the emitter current that is going down this branch, that we've sort of determined that it is going to be proportional to the envelope of the peak voltage divided by this resistor value. So I can copy this current through the current mirror and connect this branch to the IABC input of the OTA here. So this looks a little bit complicated, but let's see how this actually works. And I'll put in a few resistor values that I'm actually using. So this one is 220K, and this one is 10K. And in addition, it's optional, but you might need a small capacitor, maybe 18 picofarads or something, to prevent this from self-oscillating. I didn't have this problem, but in any practical implementation of the circuit, this capacitor will definitely be there. Maybe 18 to 22 picofarads. I want the filter pole to be, let's call this value C, but 1 over 2 pi R1C should be greater than the frequency response of the ultrasonic microphone that I'm amplifying here, so I'll say, I don't know, I want it to be around 150 kilohertz, maybe even 200. So this is kind of the functional diagram in a nutshell, and let's have a look and see how this circuit actually performs. Before we get into the details of the current mirror, it's kind of uninteresting, but for those, in case I don't get to it, I'll just give you the name of it. the Wilson current mirror. And it's just a few transistors. Mirror. Configured to give you copies of two currents. Okay, let's go to the oscilloscope and see how this thing works. Okay, so let's see how this circuit performs. So at the function generator, I have a 50 millivolts peak-to-peak signal being applied to the input of the TL074 with all the fancy feedback loop components at 4 kilohertz. And for low level signals, the amplification will be dominated by the ratio of R1 and ratio of R1 to R2. And as the input signal rises, the output signal will get larger, and the OTA gain will increase, but since it's in the negative feedback loop of the op-amp, it means it will decrease the gain of the op-amp. Okay, so let's see. R1 is 220 and R2 is 10K. Let's go to the oscilloscope and see what the output is. Okay, so I have a reading of 1.22 volts. The purple trace is the input, the yellow trace is the output. Pin 1 of the TL074. So if I take my calculator and work out the gain, and I can do it in decibels, which is 20 log base 10, 1.22 divided by 0.05 millivolts, 0.05 volts, 50 millivolts, and I get a gain of 27.7 dB. Well, let's drop that down a little bit further, see if we can actually pucker up the gain a little bit more, get the signal really low level, down to, let's say, 25. There we go. Okay. And the oscilloscope says 760 millivolts output. So let's see what that is. 20. Well, first of all, let's just take the ratio of 760 divided by 25, and the ratio is it's 30. Okay, I think my resistor, feedback resistor, is actually 270K. It's not 220K. Sorry, mistake. 270. Yeah, so the ratio of 270 to 10K is 27, which is about 30. Close enough to what we're measuring and sort of expect to measure at very low level of signals. Okay, so let's go and increase the input voltage, input signal level, to, let's go up to 200 millivolts. So keep in mind that the gain was 30. Okay, 200 millivolts. For the oscilloscope. So now we have an output of 1.7 volts peak to peak. So I'll just do it in the calculator. Take the ratio, 1.7 divided by 0.2. So that's a gain of 8.5. So it's from 30 to 8.5. It's dropping. It's suppressing, it's knocking down the gain as the signal level is rising, just as we would like it to do. Okay, so let's go to 800 millivolts peak to peak. Oh, sorry about the arm. Okay, go back to the oscilloscope. Okay, my input is kind of off the scale. There it is. As you can see, it is inverting. And output 2.62 volts for 0.8 volt peak to peak input. So what's that ratio? What ratio is that? 2.62 divided by 0.8. 3.3. So from 30 to 3.3 as the input level rises from 25 millivolts to 800 millivolts peak to peak. So it seems to be working fairly well. And as sort of one additional graphic I would like to show you is the case where we're actually modulating the input signal with an envelope, like doing AM modulation. And let's see what that looks like. That's always something interesting to look at. So we'll go to the function generator, and we'll go to the modulator menu with the 2 hertz modulation frequency, 85% AM depth. We'll keep it at that. And now we'll see what the output and input look like. Let's go to the oscilloscope. Okay, well that kind of is expected. It's changing amplitude. But let's slow the scope down a little bit so we can see what's happening on the overall envelope, and do a single shot, I think. Okay, there we go. That shows the input being triangle modulated, and there's the output, the yellow. But you can, what is obvious is the fact that the maybe it's not so obvious if, okay, those scales look a little bit better. Okay, so the peaks are almost matching up, the input peak versus the output peak of the yellow trace output channel. So what's happening is, from this graphic you can see that the input signal is changing a great deal as far as amplitude or strength, whereas the output signal of this AGC circuit is not changing as much. It's more compressed. The dynamic range is compressed. So this is kind of exactly how we would like this to work, and it appears to be working that way. Maybe for a final implementation in the ultrasound listener, between the microphone preamplifier and the modulator, the doubly balanced modulator, the MC1496. That's where it will go, and you might need a few tweaks of components. Maybe we don't want an output that is 6 volts or 4 volts maximum. Maybe we only want to feed it 2 volts, but we'll scale those things down with appropriate resistor voltage dividers when the time comes. So that's that's about it in a nutshell on how to use a well, actually, before I go, I'll show you the Wilson current mirror. That'll sort of complete the picture. Okay, well, let's just have a look and see what this current mirror circuit looks like. Okay, it's 2 transistors. And they're PNP. I don't think I'll go into a great detail of description how it works, but you can find references, I'm sure, on YouTube describing these things. So these are the V+ connections, and I'm just going to draw in the first 2N3904 that was connected to the peak detector output, which is here. It's not part of the current mirror. And another resistor there. Let's say peak detector. So these two currents will be copies of each other, but in this branch here, it is controlled entirely by what goes on in here. So these two PNPs, sorry, are a dual matched pair that come on a single chip. Just draw a little dotted rectangle around them, and they are SSM222OP dual matched PNPs. So the pin numbers are 3, 6, 2, 7, 8, 1. There. And this is the connection of the 2N. Oh, forgot something. There. That completes it. The collector of the 2N3906 is taken as the current drive into pin 1 of the LM13700. In addition, to have this thing work properly, I rigged up another sort of constant current source, not as sophisticated one as here, to drive the diode bias on the LM13700. So this is not a part of the signal processing, but a 1 milliamp bias current, thereabouts, flowing into pin 2 of the LM13700 produces, linearizes the output it reduces distortion, basically. So you can, yeah, you can Google or YouTube the use of the LM13700. There's others that make use of it and describe it. Two I can think of is YouTube channel Simply Put, and Aaron Lanterman, that describes music synthesizer circuits in great detail, that also describe the LM13700. So there you have it. Sort of modular block diagrams. Can't put it all on one piece of paper.